All right. Good morning, everyone. Good morning. Hopefully you ate your Wheaties again this morning and you enjoyed our great breakfast upstairs. Thank you for coming back to day 3. I'm Karen, if we haven't met yet. I have a background in GIS and remote sensing. I've been doing it for about 10 years now. So I've seen how the industry and the software packages have changed and evolved over that time. One of the things that I'm so proud of here at Google is that we are really starting to take big data and cloud computing from a geospatial analysis perspective very seriously. And this morning, you're going to start hearing how they're doing this inside Google Cloud. They're doing it through a new product called BigQuery GIS, which is basically special geospatial capabilities that are built on top of BigQuery, which is this giant petabyte scale ability to take tabular data and do queries with it with lightning speed. And so I'm really excited today. You're going to be hearing from the product manager of BigQuery. He's going to talk to you about BigQuery GIS. His name is Jennings. He's the product manager of BigQuery, and he's going to talk to you all about where it's been and where it's going. And I'm really excited because you guys, I think, are really going to be able to take advantage of this special technology in the next year. Get your big data into BigQuery GIS, do machine learning, which is built right in, and more. And so I'm really excited for you to harness that magic. And I'm really excited to welcome Chad onto the stage to talk to you about it and get you guys introduced to it. So if you don't mind, help me welcome Chad to the stage.
Thanks.
Thanks, Chad.
Hey, good morning, everybody. Some of you I've seen in the sessions. I've been an attendee as well as now I get to be a presenter. And so I've been delighted to hear some conversation and discussion about BigQuery in the hallways here. And I'm even more delighted and honored to show you what we've been working on. So as Karen said, my name is Chad. I'm a product manager for BigQuery. I, too, come from the navigation and remote sensing space before I came to Google. And so when I showed up at Google Cloud, there was really no attention being paid to geospatial analysis, even though Google had all this fantastic technology in other parts of the country. And so I and a dedicated group of other folks kind of took it upon ourselves to bring this forward. And so we're just delighted to bring this technology to the data and analytics space and to the geospatial industry. So essentially what you do when you take BigQuery, which I'll talk about what it is in a little bit, and when you take GIS and you put them together, it's essentially this tagline here. We're bringing very big data infrastructure to GIS in a way that hasn't been done before. So there are actually 2 presenters here. Myself, we already did the intro here, and then I have a co-presenter who's going to be playing the role of the public perception of big data infrastructure and cloud computing. And so I'd like to welcome my colleague Chompers to the stage. So Chompers is quite upset and intimidating, a little frightening, even though Chompers is 3.5 pounds. So Chompers is tameable, but he's a little like, people when they talk about cloud computing, they're like, I don't know, man, there's a lot to learn. I'm busy with my day job. So we're going to go through this, and we're going to talk about how Google Cloud is taming Chompers. Chompers is going to be a different animal by the end of this talk. All right, that's our challenge. So we know that Google's mission is to organize the world's information and make it accessible and useful. And when you're operating with a mission statement of this scale, and you have products like these that operate at this scale, you had better be good at scaling infrastructure. So these products, from search on the left to Google Cloud on the right and all this good stuff in between, have more than 1 billion users each. And so to support all of that, we have computers. We spend an awful lot of money on computers. So the top number there is actually true. It's not a typo. In the last 3 years, Google spent $47 billion on CapEx infrastructure. So that's the infrastructure that powers all of the products that we just looked at. And that number is going up, right? 3 years ago, that number was $30 billion. So we're actually accelerating our commitment to supporting all of these products. So when you're, how many people are connected to Earth Engine or connected to Gmail right now? All right, so Earth Engine, good for you. Gmail, shut it down. But I want to show you, so this is a picture of the computer that you're connected to. Now shut it down. This is in the Midwest of the United States. The buildings in the far distance house the storage and the compute. And you've seen pictures, like we have marketing shots running around this conference of what that infrastructure looks like. But I wanted to show you, A, the scale. It's about 5 football fields. And B, I wanted to talk about power for a second, right? Because power and sustainability is important to us, and it's important to you. So the infrastructure that you see in the bottom of this picture, that's a bank of generators. So if power is knocked out to this part of the country, we can actually turn on all of those generators in a remarkably short period of time so that you don't notice any service interruptions to the work that you're doing. So that's pretty important, but that's a lot of power. So let's talk about power for a second. So the PUE, or power use effectiveness, is the ratio of the total power that a data center uses to, and so that's in the numerator. The denominator is the power to serve the product. So the industry average up in yellow there is about 1.6. So almost 60%, or just about 60% of the power that industry average data centers take in is used to, like, air conditioning or HVAC, keeping the humans there fed and comfortable, et cetera. Google has worked incredibly hard over the last decade to drive our PUE down to 1.11. So just a little bit more than 10% of the energy consumed by our data centers is used for stuff that's not giving you the services that you want. We're really proud of that. We're also proud of this fact, right? A, we're efficient, but B, it's still a lot of power, right? And power is a sensitive thing. So Google also purchases renewable energy and carbon offsets to offset all of the power that we use in our data centers. So if being carbon neutral is important to you and your organization, you can check that box, at least for your compute infrastructure, by using Google products. I think that's awesome. Excellent. When I was doing the slides, I'm like, if ever there is a group to tell that story to, this is it. So thanks for that. I want to talk a little bit about what else we're spending the money on, right? $47 billion. You can buy a lot of data center for that. But we're also spending on software. And software is important because just giving folks access to like 1 trillion servers in Iowa, like, I don't know how to make use of 1 trillion servers. You need to wrap that in a service that I understand. So here's the acceleration, or here's the development of products. So Google Cloud in 2012 had 14 products. And like anybody with Superman or Superwoman eyesight can read that this one over here under the green says BigQuery, teeny little letters. Sorry for the eye chart. So here's what it looks like now. So we've launched 200 products in the last 7 years. BigQuery, Superman, Superwoman, is still in the same spot, so we've been there all along. But we're spending this on a vast array of products. And the purpose of those products are to wrap workloads in like human relatable ways. So we're going to talk about how BigQuery does that, and what BigQuery is, and why BigQuery is relevant to geospatial. So BigQuery is Google Cloud's enterprise data warehouse. So for those that don't know what a data warehouse is, you can think of it as a super big, super fast relational database. And by super big, I mean really super duper, uber big. Our largest customers are storing hundreds of petabytes of data with us, and that's tabular data, that's not imagery. And the product as a whole is up in the exabyte region. We have customers that run queries over multiple petabytes in a single SQL statement. And what's really slick about that, so that's cool. What's really slick about that is they don't have to worry about infrastructure. They don't have to call their IT person and say, hey, I'm going to send a big job through. Can you spin up a bunch of computers for me? We handle all of that automatically and in real time. So that's what the product delivers to the data warehousing market. We're going to talk about what that delivers to you. So if you have to manage any of your GIS infrastructure, which over time will be a like smaller and smaller crew of people, you have to do a lot of stuff, like everything in the gray segments on the left-hand side, right? From performance monitoring to uploading patch upgrades, et cetera. That's all time taken away from energy where you can do the real work, which is whatever analysis that you're trying to do on whatever data. And so that's the value that this product brings, right? You get to spend more time doing the stuff that's interesting and the stuff that you're good at. Google will take care of the rest because, we made the point before, we can handle scale. OK, so now, like we've covered BigQuery, pretty high level. There's a session later today where you can get a chance to play with it. Now let's talk about BigQuery and GIS together. So by launching GIS inside of BigQuery, Google became the only cloud data warehouse to have first-class support of geospatial data types and functions. So anybody here is a PostGIS user? All right, you're going to feel right at home because we use exactly the same syntax. So ST within, ST intersect, same thing inside of BigQuery. So you don't have to learn a new language. And you can execute these queries. We even built this little visualization tool. So if you feel like, hey, I just wrote a query, I want to see it on a map. You know, for all the love of good and holy in the world, let me do that. That can actually be a pretty hard problem if you've got to push stuff around between different products. So we built this little visualization app called BigQuery GIS to do that. It won't solve all of your viz problems, but if you want to get a look at the data that you just queried, it's a good way to do it. So let's talk a little bit about some other problems that come along with doing this work. That's curating data sets. Earth Engine has got a marvelous set of data sets. I've actually just come to learn about them more in the last few months. I'm really impressed. And your data catalog is better. Shane, if you're listening, their data catalog is better than ours. We need to upgrade. But we do have a lot of public data sets. And what these public data sets are superb at is being easily referenceable by your SQL code. Like if you want to use it, you don't even have to, sorry, I'm going to be a little bit rude to my host here. You don't even have to import them. You just query them. And you just write it into your SQL code, and they're there, ready. They're ready as fast as the data that you load yourself. And there are a lot of them. So if you go to the marketplace, the tag is here. Go ahead and grab your picture. I'm going to move the slide in about 30 seconds. If you go to that link and type in geo, you can see all of the data sets that have a geospatial or a geography column. All right, cameras ready? 5, 4, 3, 2. Good. All right. So we want to make doing the compute easy. We want to make getting the data into your analyses as easy as possible. Here's an example of one that we just loaded. This is all the tiger shape files rendered as roads, so you don't have to interpret tiger files for roads anymore. You can just query them. So this is 2 queries that was draw the roads in New York and then draw the roads in San Francisco. Easy peasy. Plus, the links to these queries are going to be included somewhere. Karen, if we can tell everybody where at the end of the talk so that you can start to play with it on your own. So when you put BigQuery in the world, like there's this core data warehousing platform, and I won't describe what all of those features are, but like you use SQL, it's secure, it's reliable. That's what's in this core data warehousing thing, block. And because it's the flagship product for one of the flagship products for Google Cloud, it gets a lot of investment to like put new stuff and interesting stuff around this block. So here's what I mean. There are a number of different analysis tools that you can use, or analysis capabilities that we've baked right into the platform. So we talked about public data sets, which is on the bottom left. Just above that in blue, BigQuery machine learning. So we've invented some new SQL verbs. Apparently that's sacrilege to some folks, but hey, we're going to do it anyway. But they're cool verbs. They're create model and predict. So you can do machine learning models. If you've got all of your data inside of BigQuery, you can do the machine learning right on those tables. You don't have to export them to another tool. If you do want to use TensorFlow, you can do that and then re-import the model into BigQuery and predict on it there. So we're trying to make machine learning available to anybody who speaks SQL. And then GIS, we talked about that one already. So like with this set of blocks, we're always trying to make new blocks and new types of analyses useful for people, but BigQuery really doesn't stand on its own, right? It's part of a platform, and it's part of Google. And so when you combine the strengths that we have in BigQuery with GIS, with machine learning, and then you add the rest of Google, you get combinations that are really very special. So we'll talk a little bit later about some customers who've taken BigQuery and Earth Engine and put them together into a single workflow and talk about what's possible when you do that. But I'm going to lead the audience here, and I'm going to say in this the bottom right-hand corner, what's really possible is that Google is going to try to help you remove the scale restrictions from your work. So if you want to work on a data set that's just in Montana, say, you can. If that data set is extensible to the rest of the world, go for it. You can do a global analysis. So let's start with global analysis over the water. So we've heard about Global Fishing Watch a couple times. So 20% of fishing activity is illegal. This is both bad for the environment and bad for sometimes the people on those ships. The Associated Press won a Pulitzer Prize for exposing essentially slave trade amongst ship owners as they were trading fishing ship workers. So it's really bad, and we should have a really bright flashlight that we can shine onto these remote seas. And that's what Global Fishing Watch is doing. So this is going to take a second. We're going to go from left to right on this slide. So starting on the bottom left, so that is a Sentinel radar image, or composite, Mediterranean. And each of those little white dots is a ship. So vehicles are supposed to, anything over 300 gross tons is supposed to have the AIS, was the Automatic Information System, and so broadcast their position. But nefarious captains will go and cut the wire to the transponder or throw it overboard or whatever, but they don't want to be broadcasting where they are. However, you can't hide from radar. So you can get the position of every ship on every ocean, everywhere in the world, with one script. Okay, that's a wow moment, right? You can do it over the entire ocean. Now let's do another one, right? You can also, in BigQuery, you can ingest all of the AIS data for the whole world, and you can diff those two data sets, right? So you've got the people broadcasting, those are the good folks. You've got everybody on the ocean, which is the good folks plus the bad folks. You diff that, and you get, on the left-hand side, the bad folks. It's not as simple as that, right? They have to do a lot of careful work to really make sure that that result is hit. But they're doing this over the entire globe in single runs. That's awesome. Let's talk about a problem on the land. Same thing, global scale. So S4 Analytics is looking at the problem of variability of food production due to climate change. And that's what the heat map shows here. So the hotter that heat map, the more that area, it's, in this case, wheat production, is susceptible to variability for climate change. So now with variability in food production due to climate change, there's variability in our food supply. The problem is there's not that much variability in our population growth. So there's a problem here. And so what are we going to do about it? Well, we're going to model the snot out of it and make sure that policymakers and the financial markets understand this. And so what S4 has done is up in the top corner here, they're looking at all of the agriculture land across the entire globe, finding the number of hectares that are producing various types of crops, like soybeans, wheat, et cetera. They're then taking that and putting it into BigQuery and combining it with the weather data that we already have as a public data set in BigQuery to make predictions about what next year's food production is going to be. Right? This alerts, as I said, financial markets. This also alerts policymakers to say, hey, there's a drought in, there's a drought in the Midwest of the United States. There's a drought in Australia right now. Those areas are not going to produce as much. We need to make sure we have food to ship around, et cetera. So two examples of global scale on the water, global scale on the land. Now, if anybody's from the Midwest, an equally important region, not global scale in Chicago. I wanted to tell you about this one. This use case doesn't involve Earth Engine, but it is really interesting. This is the last use case we'll go through. So our customer, Geotab, is a telematics company. And they put these little boxes in vehicles. And UPS is one of their customers. So they have hundreds of thousands. They actually have about 1.2 million vehicles in the United States and in Canada. And those boxes record position, velocity, acceleration, air quality. We'll talk about that one at a different time. That's a really interesting application. And a host of other measures. And so, as UPS, you want to know where your fleet is, and you want to be able to optimize routes, et cetera. But one of the interesting things that when you mine that data and combine it with other data sets and do it at large scale, you can make this application on the right-hand side of your screen. And what this is, it's a machine learning algorithm. This was all done with BigQuery GIS and BigQuery ML. So let's pretend for a moment that you're all city planners in Chicago. And on the right-hand side, you can dial up temperature, the visibility along the roads, whether it's precipitating. You dial those up and you hit run predictive analysis, and they will tell you where the hazardous driving behavior will occur based on historical data and based on the weather. And so you can use that to say, well, I better pre-position some sand, or you can join that with school locations to make sure that you've got better signage up around schools. So they're actually selling this solution to cities around the country right now. Nice thing about the scope of this is that if their solution works in Chicago, it'll work in Miami. If they have data for it, it'll work in Kathmandu as well. So the point is, we want to take the brakes off the work that you guys are doing. And the brakes are not there because you lack imagination or skill. You have plenty of those qualities. The brakes have been on because the infrastructure wasn't there to support your abilities, and now it is. So chompers, he's our friend now. Google is taming him so that you don't have to. And I really feel like, so hey, good news, right? Chompers is a happy dog. But I really feel like we're in an inflection point, not too dissimilar from Street View about a decade ago. So when Google launched Street View, we had the ability to go out and take a lot of pictures, to geo-register those pictures, and render them in 3D, right? For 2007, that was awesome. Nobody had done that one before. We didn't have the ability to look at those pictures and extract information from them. We couldn't tell that this was the Rue de Saint-Germain. We couldn't tell that the brand Promode was at this intersection. Now we can, and we can scan those images, and we can use that information to make maps better. Like if you're searching for Promode in Paris, you can find it because we saw the sign. We can also make traffic rules better, right? There's a traffic sign off on the right-hand side. We can make sure that whatever that road is, has the right directionality in our directions APIs. So we've really, being able to dive into this data at scale has enabled us to make new services available to you and to the rest of the world. And I really feel like GIS is at the same inflection point, right? Because the ability to scale the way you can with the tools Earth Engine and BigQuery has really not existed in the world before. And so I think we'll all look back, 5 years from now, we'll look back at the 2018 to 2020 period and be like, yep, that was an inflection point. I can do new analyses that I could not do before. I can do them now, and I don't have to worry about the infrastructure. I just do what my imagination commands. So with that, I am exceedingly excited to see what you all come up with. Thank you very much for your time. So if you think that listening to a product manager who's worked for the last 5 years to make this happen is like maybe a biased sample, you're right. I invite you to try it for yourself. There's a session today. There's a session on public data sets today. These links will be supplied somewhere on the website. So kick the tires. Give it a try. If you don't want to pull out your credit card, try that sandbox thing. No credit card needed. Right on. Thank you.
Thanks, Chad.
I'll give it to Carly.
So we're going to kick off now with keynote and lightning rounds. And if you're doing a lightning round this morning, if you can line up over there as before and meet up with Lena. So I have the honor today to welcome Carly Vynne Baker. Carly has done amazing work in the Brazilian Cerrado with maned wolf and giant armadillo and hard to imagine species, right, as we're sitting here in Mountain View. She's now thinking bigger picture, and she's going to speak on the global deal for nature. Please join me in welcoming Carly.
Good morning. I think I've caught what I'm going to call the Google buzz. And I'm attributing this feeling to high levels of exposure of all these Googlers this week, because they've got me thinking that I, too, can help shape the world in an important way, and in a way that didn't seem possible only a few years ago. Anyone else have this buzz? I think too often in conservation, we're limited by thinking about what seems possible today. So what if we just take a few minutes and instead imagine the world that we want to live in? What does this world look like? Well, surveys from all corners of the world show us that no matter who you are and where you live, it likely is not a world without wild places. The world most of us envision, however, is not the world that we are creating as we go about our daily lives. The world most of us envision will take more effective conservation action. Rebecca earlier highlighted the power of using Earth Engine to set ambitious goals and then use it to monitor them. Previously, we had relied on an entirely piecemeal approach at assembling habitat data for tigers to understand what was happening across their range. Now, in matters of days, we could do a range-wide analysis and get feedback. So our team started thinking about how we could scale up from working on a single species to even more ambitious targets. And it turns out that if your goal is to save not only tigers, but the rest of life on Earth, we're going to have to think about much bigger ambitions, much closer to half the Earth than the 15% that we have formally protected today. And you may be from an indigenous community that this has been a central tenet of how you've been managing lands for generations, or it may be that this is a big, audacious idea which seems impossible. But it's a big idea, and I think that it needs some exploring. Is a world half protected necessary? Is it even feasible? And if we're going to think about protecting more land, where might we go about this? So using this map of the world, which I like to call the map of the world as nature might draw it, or the world's terrestrial ecoregions, and you can show the animations, we conducted a review of hundreds of conservation plans that had been put together by local and regional people from around the world, and they showed us that on average, between 25 and 75% of each region needs protecting to meet goals to provision ecosystem services or meet biodiversity targets. So on average, about half. And this is likely a vast underestimate for many regions because only 11% of these conservation plans were even thinking about climate adaptation. So if half may be needed, sorry, back one, please, then the next question is, do we have the remaining habitat to do this? So using the compute power in Earth Engine, we were able to assess the amount of remaining habitat in each of these ecoregions. And the answer provided us quite a mixed story. For 22% of the world's ecoregion, shown here in red, on average, they have only 4% remaining. Clearly, getting to half is not a realistic or even a desirable goal in these places. For many of them, 10% protected would be a win. But for other places, more than 500 ecoregions shown in green, they have enough remaining habitat or may already be there in terms of protection levels. So following on the heels of this assessment for biodiversity and what's necessary and perhaps feasible, we got some big wake-up call from the IPCC, who less than a year ago issued a report that was very clear about imagining a world with 2 degrees temperature warming. And this world, they told us, would be a collapse of the world's coral reefs, sea level rise of 3 to 10 feet, permanent drought covering a quarter of the Earth, and by 2050, maybe 100 million climate refugees. The message for the future that most of us envisioned was that we need to stay below 1.5 degrees. And the new climate models were showing us that in order to do so, we need to leave about half of the terrestrial realm intact. And so we argued that for the Paris deal to be successful, we need a deal for nature. The two agreements are interdependent. So last spring, we were able to start looking at using, again, Earth Engine to assess remaining habitat out of protected areas. How could you set these more ambitious targets, both to represent life on Earth and also help sequester as much carbon as possible? We could bring in a variety of biodiversity schemes, everything from key biodiversity maps, maps of range rarity, threatened species, you name it, we put it in there. And thanks to Earth Engine, we're able to assemble in weeks kind of a living data set of how we might go about this. The paper was accompanied by a petition asking governments to commit to these new ambitious targets. And it's to date gathered 2.9 million signatures from 92 countries. We're aiming to have 20 million signatures by the time the leaders meet a year from October to set new targets. But we also realize we need new and creative solutions to saving nature that are outside of the traditional protected area realm. Even doubling the current system to 30% in the next 10 years won't be enough. So we're proposing a system of climate stabilization areas, which are largely intact lands outside of the protected area system. And literally just yesterday, we finished an analysis using a new map of carbon biomass that helped us identify and rank potential carbon areas that in turn would need the funding and management capacity to keep the world below 1.5 degrees. And I want to show you just a visualization, and just for the terrestrial realm for now, unfortunately, at what a global deal nature could look like if realized. So while global visions may be helpful, the reality, of course, is that achieving them will and should entirely depend on the hearts and minds of people living in every corner of the world. Achieving 30 or 40 or 50% for nature depends on tens, if not hundreds of thousands of people sitting down, looking at maps, and deciding if and how they're going to conserve the landscapes in their backyards. But the pace of change in our world is so great that we can't keep up using traditional methods and tools. And so back home where I live, in Cascadia of Washington State and British Columbia of Canada, we're working, and in this area also change is rapid, from population growth and immigration to climate change impacts and wildfire. So we're developing a conservation planning toolkit that will sit atop Google Earth Engine and allow us to make scalable, dynamic, and climate-smart conservation plans. A prototype of this tool will be presented by Andrew Shirk in a breakout session tomorrow. But here's a brief preview of some of the functionality. So we were able to create a high-resolution land use map for the first time that crossed the international boundary, which was something that our managers here had been telling us we needed. We are also able to develop landscape integrity layers that are dynamic, and so that as managers set goals, they can be adjusted based on the reality, such as fires that are occurring on that landscape. And then finally, we know that the landscape is changing due to climate, and we need to adapt. So in this case, we're looking at, for example, our shrub steppe biome and how that might shift with climate change, and how we need to develop adaptive conservation plans. And then we can even overlay and consider how our actions on the ground and the human footprint are going to affect the ability of this biome to shift and the species within it to shift over time. So global visions might be necessary to push the envelope, but it is really at this local and regional level where most decisions and outcomes will, of course, be made. The work in Cascadia, like that showcased by so many of you this week, is what will propel an implementation of a global deal for nature and give us a shot at implementing the vision that we all imagined. So thank you very much, and I just want to call out in particular Tanya Birch, a few people who are in this room. Tanya Birch has been a co-conspirator in all of these projects. Andrew Shirk developed the Google Earth Engine models for Cascadia, and David Treese developed both the ecoregion websites as well as the Earth Engine app for Cascadia. Thank you.